This tutorial is going to talk about bisectors and triangles, and this section kind of gets a little crazy. So what we're going to first talk about is what this section is mainly focusing on. We have a couple theorems that we need to look at, and these are theorems I strongly suggest that you put on your theorems and postulates page. So we're going to first talk about theorem 5.2. So this theorem also has a special name, Perpendicular Bisector Theorem, or PBT. And if you want to get the exact definition for this, it is on page 265. So we're going to start by looking at this theorem with a segment. We have segment AB here, and perpendicular bisectors do two things. They create perpendicular lines, which means 90-degree angles, and they bisect or cut in half whatever it is they're cutting in half, a segment or an angle. In this case, it's this segment. So I'm going to go ahead and draw this perpendicular bisector here. And first of all, we're going to estimate where about the midway point is. Looks like it's about here. I'm going to make sure that I have a right angle for the perpendicular part, and then I'm just going to continue this all the way through. So just like this, arrow here, and at the other end as well. And we are going to call this C, and this point here D. Alright, so we have the perpendicular part taken care of right here in red. We have our right angle. And we also know that DB is congruent to DA because I bisected that segment. So here's what this theorem says. You first have to have this situation happening before you can actually apply this theorem. And what it says is pick a place on this bisector, CD. Pick a point anywhere that you want. Let's say I pick right here, okay? And I call him X. What the theorem says is that that point is equidistant, in other words, equal distances, to either endpoint. So in other words, this segment here, oh, that is a bad segment. Hit with the program, Miss Larson. Jeez. Let's just do a line. We'll say that this piece is congruent to this piece. And that is true for any point that you pick on that bisector. And that's going to come in really, really handy when we start seeing problems that deal with this. So let's pick another point. Let's say I pick a point down here. Okay. Once again, because this point lies on the bisector, the perpendicular bisector CD, it is equidistant from B and A. So good stuff, good information. Make sure that you have this theorem on your chart. So let's take a look at a problem that uses this information. In this picture, I have a quadrilateral, figure ACBD, and I know that CB has a length of 5 and AD has a length of 6. And even more so, the important parts are the parts right here. I know that I have a perpendicular segment, CD, or AB, just depends on how you look at it, with two congruent pieces. That means this is a perpendicular bisector. So CD is bisecting AB. And that's very helpful because we want to know two things. I want the length of CD and DB over here. So let's use this theorem to help us do that. So just focus on the upwards triangle. I'm going to highlight it in green. This is the triangle right here that we are going to look at first. So if CD is in fact the perpendicular bisector of AB, then I meant to say that that's not CD, but CA. I'm sorry about that. Let's fix that up. So CA. So because this segment over here is congruent to this segment, both with the red tick marks, then that follows my theorem 5-2, the perpendicular bisector theorem, and then this side, CA, must also have a length of 5. So then how do we find the length of DB? And the answer is the same exact thing. Notice that CD once again is your perpendicular bisector, and D is just a different amount of units away from AB than C is. And that means that these lengths over here are going to be different, but they're going to be congruent to each other. So AD is congruent to BD. But notice something that I was trying to explain. This piece right here is not necessarily the same length as this piece here, and that's okay. As long as you have a perpendicular bisector, the point is somewhere on that bisector. You've got congruent segments going somewhere. So I can go ahead and fill in here that DB has a length of 6. So the next theorem that we're going to look at is theorem 5-4, Angle Bisector Theorem, or ABT. It's on page 266 if you want the exact definition. And we're going to look at this from a picture point of view. So here we have an angle ABC, and when we talk about an angle bisector, it means that we cut the angle directly in half. So let's go ahead and draw a bisector in here. And it should look something like this, and we'll give this the letter D. So because this bisected the angle, this angle here, angle CBD, is congruent to this angle here, ABD. And although they don't look exactly identical, I am freehanding this, so just be patient with me. So here's what this theorem says. What it says is, let's say you have a point and it's on the bisector BD or ray BD, then what it says is that this segment right here is the same length as this segment here. And that's pretty cool information. But what's wrong with it is something very special has to happen in order for this theorem to be true. And that is that these are perpendicular distances. This theorem cannot work unless you know that these are right angles, because I could have this segment, the lower one, be here or here or here or anywhere like that. So that theorem would not exist unless we had that specific rule. So you have to make sure that when you connect a point on the bisector to another side, that you make a right angle. So let's try that in one more time. So let's choose this point here this time. Once again, I'm going to see if I can get this Angle Bisector Theorem to work correctly. So when I connect this point to side BA, I'm going to make it so that it makes a right angle. When I do the same thing to the other side here, that also gives me a right angle. And this segment is congruent to this segment. So that's what the Angle Bisector Theorem says. Let's take a look at a problem that uses this information. So let's say that we have all this information. We know that these are perpendicular segments and that they are congruent. So by the Angle Bisector Theorem, those two red segments should be congruent to each other. So if we have this instance where this piece is 5x and the other is 2x plus 24, I can set up an equation to solve for x. So 5x is equal to 2x plus 24. That is what congruent means. If this segment is congruent to this one, this must be true. So we solve this. We're going to subtract 2x from both sides. I'm going to get 3x here to equal 24. Divide both sides by 3, and x should be equal to 8. Now, that's grand and dandy, but what if I did something wrong? How can I check my answer? Let's go back in and plug in 8 for x. So for this guy here, let's do 5 times 8. We substituted x with 8, and that gave us 40. Now, if this is completely true, then when I plug x into this guy here, I should also get 40 as well. So let's do this. 2 times 8, and then when I'm done with that, I'm going to add 24 to it. So 2 times 8 is 16 plus 24, and that does happen to be 40, so this checks out. I know that I did this correctly. So that concludes this tutorial, and the two big theorems that we learned about were the perpendicular bisector theorem and the angle bisector theorem. Please make sure that these both go on your theorem and postulate charts.